Welcome back. This is the second part. This is part two on our lecture on the basic mathematical modeling of immunology. Okay, so this is part two of this mathematical model for infected cells interacting with virus and interacting with uninfected cells. So we were discussing the basic reproductive number for this basic model, and the advantage of the basic reproductive number is that now we can establish a threshold for dynamic behavior. This is formally referred to as the qualitative behavior of the model. And this brings back these ideas of the model being at equilibrium. So there are these points at which the rates of change are zero, meaning that the state variables do not change when the system is settled into this point. And very importantly, there is the notion of these equilibrium points, these steady states, being stable versus being unstable. And for this basic model, the expression of R0 is what the expression of R0 is what we have here um, in red. It involves lambda, beta, and k in the numerator, and d, a, and u in the denominator. But also, this ratio or this number establishes when we have the stability of one equilibrium point that we're going to call here the endemic um, steady state or equilibrium versus the stability of another equilibrium point. So if on average, each infected cell can give rise to more infected cells. Something that is represented here. You see one cell is invaded with a virion, and the virion, this is something that's called burst. The cell bursts into more offspring of virus, and somehow it manages, this one infected cell manages to not only produce more offspring of virus, but effectively go and invade other cells. So this is an illustration in which one infected cell yield three newly infected cells. And so if that is the process, that on average one infected cell can produce more than one infected cell, then we're going to have that the infection here will sustain, will actually healthily, will grow very efficiently. On the other hand, if on average one infected cell um, fails to give rise to another newly infected cell, then what we're going to have is that the virus population will go extinct. So it's an extinction of virus. Okay, so this first scenario has to do with something that we call the endemic steady state or endemic equilibrium being stable, while the second scenario has to do with something in which we say is infection free, is free of infection. Sometimes this is also called disease free, is free of disease, meaning that it's not possible for the infected cells to establish themselves within one typical host. So we have stability of endemic equilibrium if R0 is greater than 1, and stability of the disease-free equilibrium if R0 is less than 1. Okay, and here is some little illustration for you. So in summary, what we just mentioned, we can write more um, we can write some expressions, right? So this is the basic model that keeps track of the size of uninfected cells, the rate of change in the size of infected cells, and the rate of change in the size of virions or amount viral load. Okay, the basic reproductive number, as we were mentioning, in the numerator, it involves uh, the terms that are basically the growth terms of each of those rates of change, right? So here you have a gain in terms of lambda, a gain in terms of beta, and another gain led there by k. However, the decay terms, which are d, a, and u, they all appear in the denominator. Well, it turns out that when R0 is less than 1, then this equilibrium point is stable. This is what we were calling disease-free or free of infection, because here there are three entries, right? And in this scenario, what we're saying is that here in this scenario, what we're saying is that x, how can I write this? So x, when this is true, x would converge to the term lambda over d, uh, but y would converge to 0 and v would also converge to 0. Okay, so as t goes to infinity, x of t approaches this value, while y and v are approaching 0. That means that virus becomes extinct, and there is no virus. There is nothing to invade the cells. There are no infected cells. On the other hand, if R0 exceeds unity, then this other equilibrium point is stable. And so when R0, you can notice here that when R0 is greater than 1, then R0 minus 1 is positive, right? That's an implication. And so what this is telling us is that X, in this case, X converges to lambda over D times R0. Now the denominator is the product of D and R0. Y converges to this other term, du times R0 minus 1, which is a positive quantity, divided by beta over k, and then V converges to this other quantity. So what we're seeing here is that the endemic equilibrium steady state is when stable implies that state variables are converging to levels that are positive, okay? Positive levels. Okay, so let's see. Here are some illustrations of these qualitative scenarios. This is the stability of the disease-free or the steady state where the host is free of infection. And what you see here is a numerical simulation or numerical solution of the model with parameter values that were chosen such that R0 would be less than 1. So the curve you see in red is the curve of the uninfected cells, and then there are two other curves here that are crashing to 0. They're converging to 0. So I want to note that you're looking at these numerical solutions as functions of time, on times on the horizontal axis, and for these type of models, sometimes you will end up with quantities that are in certain scales, rather large, and it's convenient to plot the same solutions in a using logarithmic scales. So the same numerical solutions now displayed on, this is what you would call a semi-log plot. You still have time on the horizontal axis, but here the vertical axis is now the logarithm. Okay, so these curves, basically what we're seeing here, the red curve is x of t, so this would be the natural logarithm of x, and this curve here in the middle is the, you write log instead of ln, but it doesn't matter. So this is the logarithm of y, and then the other curve would be natural log of v. Okay, so that's the same values but displayed on logarithmic scale. Sometimes you have a much better resolution. Okay, and what you can see clear in regular scale, those curves are approaching 0 rather fast. There's almost like an L shape there. But when you use the semi-logarithmic plot, then you can see that decline towards, these are values of order 10 to the minus 11, 10 to the minus 7, right? So those are approaching 0, and you can have a better resolution. Okay, and for purposes of reproducing this yourself, then here are the values of initial conditions and also the values of parameters, and you can verify that if you plug in those values of parameters into that formula of R0, then you're dealing with a value of R0 that is below 1. And last but not least, this will be an illustration of that qualitative scenario in which the endemic equilibrium is stable. So X well, you will see. So these are numerical solutions of the mathematical model. Now you can see how the virus, this is in regular scale, the viral load rises up to a high level there, and then it settles into, they all settle into some positive equilibrium level. This is a plot in regular scale, and if we consider the same values now on logarithmic scale, this is a semi-log plot, then we have better resolution, especially of what's going on here, right? So there is an initial interval of time in which the system is trying to settle itself, and after some period of time, then you can see how all solutions converge to positive values, right? So these positive levels are what we call the endemic levels of infection. So the initial conditions and parameter values used for um, computing these numerical solutions are specified here. So you should definitely you're encouraged to use LSOTA and to code up these equations and replicate these very same solutions. And also you should try doing the regular plot and the semi-log plot. And this concludes our lecture in deriving a basic model for immunology, the foundation of mathematical immunology, if you will. Thank you.